Thank you everyone for coming. It's a great place. I've never been in the office here. So my name is Elena. I work at Confluent, and today I would like to talk about a topic which has been fascinating me for quite a while, anomaly detection. And anomaly detection is actually a part of our life in so many different ways. And I bet actually also in this room and overall in the city, there are so many mechanisms to detect anomalies and prevent some issues. And it is complex. Sometimes it doesn't work, like we have seen, I guess, last week in Spain with electricity issues. I guess I bet there was a lot of things we should have prevented and detected those issues in real time, but it didn't happen. So let's talk about anomaly detection. And since I prepared this presentation before than last week, I'm using a bit of a different example to start with. So let's imagine we work for a company that builds a navigation system for the cars. In fact, I actually worked for one in the past. But our imaginary product is installed in many different cars, and we try to recommend the best route which we have based on the data we collected and all the smart techniques which we have. But every now and then, some driver takes a different route that we proposed, and maybe they wanted to have some kind of scenic detour or something else, nothing unusual. One driver, whatever, maybe they have a shortcut which is only available for them. But then another driver makes the same decision, and another. Still, we don't know. Maybe it's random. Maybe there is a seasonal pattern. Let's say some people try to take a different route during the school drop-offs hours. I have no idea. I don't have kids. But nothing to worry about yet, till we realize that at some point of time, almost no one takes the route which we recommended and suggested. So then we are starting to ask, is there any issue? Is it a construction or an accident? Should we alert others? Should we replan the route overall? And anomaly detection actually helps us to recognize these unexpected shifts in behavior of people or other things, whether it is a road traffic, server performance, maybe some financial transactions, or server readings. It all starts small, but then it starts to mature. So in anomaly detection, we can actually differentiate unintentional anomalies and intentional anomalies. Both of them matter, but unintentional anomalies are usually due to errors or some kind of noise in the data collection process. We still want to avoid them because they actually bring imprecision into our data, so we want to avoid them as well. Intentional anomalies are real troublemakers. Those come from some specific actions or events. It can be something which is actually totally makes sense. For example, there is some holiday, and that's why there is a spike in the purchases which people do. Or maybe that unexpected purchase on your credit card is actually an anomaly you want to avoid because someone else used that information about your credit card. So anomalies are complex, and to also understand why it's actually complex to solve, let's look at three different types of anomalies. We might have a point anomaly. This is kind of a global outlier, this single individual event within the rest normal data set. Again, someone, or maybe it's a person, maybe it's you who are buying that very expensive present, or maybe it's actually an anomaly and someone else buying using your credit card details. Otherwise, the data looks normal, but there is a spike in the purchase which you actually don't usually do. Then there is contextual anomalies. This is where the data overall looks, or that particular record looks fine, unless we take into account a context. For example, the electricity in your home usage. It happens that there is a spike of using electricity in the middle of the day, where usually you are not at home. And we cannot really blame the cats of watching TV at that point of time. So, and there is another anomalies which we call collective anomalies, where the data overall is fine, per instance, but when looked together, it deviates from the norm, and this can be that a lot of cars decided to take the same route because of some accident or something else. To solve the anomalies, we can use different types of models. We can use classification models, which is trained using the labeled data set, and this is supervised machine learning. We can use unsupervised learning, where the model itself will figure out how to group the items. Or, and this is quite important for us, we will go the third route. We are going to use the time series models. So we are going to use the models which actually assume that our data is a time series data. And we are going to do that because streaming data, the data which we are talking about, the data which comes from some kind of bank transactions, or the data which is streamed from IoT devices embedded into our cars, or maybe they're like at our homes, it's usually a time series data. Most often in Apache Kafka, we have a time series data. And we have some specific mechanisms to solve that. So the fact that we are working with time series data impacts the choice of the models, of the algorithms which we are going to use, because technically the variables which we have, they kind of create dependencies between the data points, and then the data points evolve depending on the previous data point in our data. So, the methods which are often used in time series anomaly detection are visualization, and then statisticals and ML models. We are skipping visualization away. This is probably more relevant for the previous generations of analyzing the data, but we are going to look into one statistical model and one ML model. And here, overall, the whole concept which we are going to use kind of can be simplified with these graphs. So first, to understand where anomalies are, we predict the expected behavior. Then we see the actual behavior. We can understand the delta between the actual behavior and kind of how much the actual behavior deviates from the prediction. And finally, if we define some kind of threshold to like where is kind of the difference which matters for us, that actually this is anomaly. And once we have that, we can detect anomalies. So this is kind of overly simplified. And also depending on some different use cases, maybe not everywhere applicable, but this is kind of how we can detect anomalies. And we are going to use two different approaches, but in short, it will look like this. Assuming that we get some data, we are going to take and bring the data to Apache Kafka topic. We are going to use Flink to analyze the data, and here I'm going to use those two types of models. One will be ARIMA and another one will be LSTM model, and then we will output the data to another topic. So the whole magic will be happening in the Flink area. And the first model which we are going to start with, which is actually a statistical model, is a model called ARIMA. Anyone heard about this model before? Okay, we have actually 3-4 hands. Amazing! This is amazing. So, yeah. So, ARIMA stands for Autoregressive Integrated Moving Average. I can complain for days about the names which people give to things, because to be honest, those names not always reflect what exactly is happening. But let's look one by one, because then we understand how exactly we analyze and try to detect to try to predict the future using ARIMA. Because technically with ARIMA, we are trying actually to think about the future. The anomalies then we predict by comparing the actual data to our prediction. So, and there is quite a lot of math. So those actually the formulas which are not far from the real formulas used for all of those pieces. But I'm not going to share you math because you will fall asleep within 5 next minutes, and actually I will fall asleep as well probably. So I'm going mostly to show you like history, which can explain where the whole concept for ARIMA comes from. And it starts all with autoregressive part, and starts with George Udny Yule, who in 1927, quite long time ago, actually was observing the spots on the sun. So those spots were coming on some kind of periods of data, and scientists were debating, is it truly like periodic behavior, or because it was actually having those cycles were not equal to each other, that's just randomness that looks like a cycle. And at that point of time it was considered like, okay, a year has a certain number of time, like the amount of time which Earth needs to go around the sun or around itself, it's kind of more or less fixed. So that is a cycle, but everything else might be not. And this statistician actually proved that it was a cycle, and he created a model, mathematical way to model a noisy periodic data. So he actually stated that the world is not perfect, and our data or the whole thing can have a bit of randomness in it. So his work was a basis for the autoregressive model, and generally it really helped us to work with time series analysis. So that was model number one. The second one was what is called moving average, and it's attributed to Evgen Slutsky, who in the same year published a paper where he said that purely random disturbances, so kind of random shocks in data which we observe, when passed through a moving average process, could look like a smooth, wavy cycles. So the whole idea was, if we look at the data, we try to predict the next stage of the data, we make an error, and we look at those errors which we have in the data, and then we actually send them through the moving average, not the data itself, but the errors which we made in prediction. Then we start making sense of those errors we can make. So the errors have their patterns. So here we are looking at the errors of the prediction, so our prediction mistakes, and they influence how we think about the future data. So those two things were quite important to analyze the data. And then two other scientists, George Box and Gwilym Jenkins, I probably mispronounced his name, but they actually started to unite those two approaches under one umbrella. But they ran into a challenge because both autoregressive and moving average models, those mathematical models, only work with stationary data. And there is a tricky thing with stationary data, and it's kind of a complex thing to maybe understand from the start, is that our data with which we work with on a daily basis, it's not stationary data. It has a trend, it has a change. But if we want to have stationary data, it should be a data which kind of only very lightly changes, and it kind of remains around the mean value all the time. So we can transform our data and kind of apply the differencing between the values, and in the end create some kind of this internal state of the data. So how it works? For example, we have stocks, and the stocks changes from one day to another, and it kind of has a trend. So this is like a stock value, real-time value. And then we can apply differencing, and we can actually, instead of thinking of the data in terms of, on the first day there was like stock price was 100, on the second 102, we actually try, like we take from 100 to 100 and we get 2, and for the next day we get 3 and 4. So yeah, I might have made a mistake here. But anyway, so you got the idea. So we are trying to change the way how we perceive the data. So we are taking only the difference between the values. And in the end, we have more or less a stable line. And if we have to do it multiple times, if it's still there is much of a trend here, it goes all around, it's not stationary, we apply the second time this kind of differencing. And there are different ways how we do it in different models. But overall, we kind of flatten the data. We only take care about this difference in the trend, not about the value itself. And once we do that, we can use autoregressive and moving average together under one umbrella. And this is how ARIMA more or less works. It takes into account about kind of the mistakes which we are making, also about having this kind of randomness which comes from in this autoregressive, and also kind of manipulates the data to work only with this kind of differencing part. ARIMA models help a lot with that complexity, because I think it's kind of not super easy to do on our own, for sure. So now coming back from to the real-time streaming data. So as I mentioned, we are going to use Apache Kafka first to bring and to work with the data. At this point of time, I want to ask how many of you worked with Apache Kafka? Maybe I should have asked how many of you didn't, but I see that actually we do have some hands which were not raised. So, but majority of you know Apache Kafka. This is a platform which we use to direct our data across multiple systems we have, to organize the whole data streams and all the rest. We also have Apache Flink. And I wanted to ask how many of you used Apache Flink? We have some hands. We have some people who doubt. I'm sure there is more. So great, thank you. I think there is some number of people who know Apache Flink. If you don't know, Apache Flink is sitting at the heart of real-time data platform. It is capable of ingesting both unbounded streams. So, for example, that real-time data which comes either from our cars or from the stock market or something else, and bounded historic data sets. And then it lets build a pipeline to continuously consume, transform, and route the data in near real time to whatever system you later need that data in. We can also with Flink join those real-time data with some historical data. This is quite a powerful and common use case. So now let's focus at this part where the whole ARIMA magic happens. And this is how it will look like. I took the data from the stock market. It's kind of like price by minute, more or less like the sell price. We start by creating a Flink environment, read the data from Apache Kafka. Then we are processing the data based on the windows. And for a given window, we will run anomaly detection. We will also need the model, this ARIMA model, which is statistical model. We will come to ML models yet. ARIMA model on this data. What I periodically tried to retrain the model in my experiments. But generally, you can also find a good balance between training it like more frequently, less frequently, based on your needs. And based on that, we predict the next values, compare the prediction values to actual data, yield the results, bring it back to Kafka topic. So this is the plan. Also, like this is more or less the data in simplified way how I had it, and I was looking always at the close value for a given stock price, how it was sold. A bit of Flink. This is the data streaming API. So I consume the data from a source, then I add a key to the data, and then I am running this tumbling processing time windows and calling the anomaly detection. So this is just Flink logic. We execute that part I do consume the data if you're curious how the source looks like. This is just like a Kafka source and Kafka sink. And in the anomaly detection part, honestly, I'm here relying on ARIMA model. So based on the window which I have, checking the number of items which whether I have or don't have enough, then training the data. So I actually here I had to simplify it, but I do have the logic which determines if I want to retrain the data, and when I want to retrain the data, I'm using this auto ARIMA. So this is like there are several libraries which can help you with the prediction using ARIMA, and they have pros and cons and some extra complexity. This particular library is quite friendly because actually it really helps with determining all the parameters we need, and it tries to help to, for example, how much we need to do that integration, differentiation of the data to simplify it, to be kind of a more or less a flat line. So, and after that, we predict based on that model and compare the actual value to the predicted one. And then we get the results based on that, if it's anomaly or not. So this is ARIMA. The funny thing is, and this is kind of was unexpected to me because I was submitting this talk for DevOps UK. And then at Confluent, when later I was already working, I realized that we actually are implementing ML forecast function, which uses ARIMA for that. With Confluent, we do it in way smarter ways than my particular simple example. And we also kind of give a time and also possibility to train the data first, and then automatically we start prediction mode. Also, if you are at current in 2 weeks, there will be a creator of that ML forecast function there giving a talk, so you don't want to miss it. So this is the ARIMA model. The second model which I tried is a long short-term memory. Which sounds very interesting. So it is, the core idea is to remember important information for long periods of time while forgetting what isn't useful. And how it works. So it works also with sequence of data. So here we again kind of a sequence of data. It's often used actually for some text prediction, but also with other types of sequence of data. So I mean, like once I kind of try to put the letters, it's easier and easier to predict what will be coming next. So here I have once upon a time. And the whole idea is that when we are predicting the next character, we kind of are basing our judgment based on the previous value, not only one value, but far like in front. And sometimes we need to define what is more important to remember and what is less important to remember. So LSTM is a special kind of recurrent neural networks. And in a basic RNN, for each step in a sequence, like for example, when we are taking some of the letters, we produce the output, but then, so the result, but then also there is a hidden value which then goes to that node of an RNN, which helps us to decide what is the next value. But the problem is, the basic RNN, they forget too quickly. So they took that hidden value, which was produced after one letter, and then kind of they are lost. So with LSTM, we introduce extra memory. So in a node, we have a memory that actually now also gets additional information and sends that additional information to the node function when we need. So in the node function now we have three things: the data which comes of like the letter itself, then we have the hidden information from the previous a calculation, and also we have the memory. But the memory itself, we kind of also try to train the model in a way that we have extra gates. We have the gates. They are gates for remembering extra information when it's needed, then forget gate, should we forget something out of the memory, and also output gate, what part of the memory can we and should we use to generate that kind of like to take from the state into the function. And this is, in a way, so we train the model. This is weights and biases, like in any machine learning model we have. And the idea is that we train those weights and biases, those gates, to react correctly to the text which we receive. For example, if you have the cat, which was a very small set on the table. So when we went to the word set, and it's very similar to word cat, it's kind of, we might think that set and cat, maybe we should forget the cat, but no, LSTM will be trained, if we train it on the text, that actually the word cat is important. We should continue keeping it in our memory. So anyway, so this is how LSTM works, and it's more complex than just a normal RNN, but also it's designed to have that complex patterns where earlier inputs matter a lot. And it's widely used in the sentence prediction and also overall kind of the predictions which we might run into. So it kind of fits also quite well into predicting that sequences which we have. And here again, I used two Kafka topics that was not right now the stock information, just kind of a sequence of the records. And what I do, I read the data from a Kafka topic, process it in Windows. So with LSTM, we actually care about the sequences of the records. So it's not only one value. We need to have a chunk of the information, because we look at the sequence and we compare the sequence and we try to recreate that sequence based on the information which the model has. So, and that's why we actually, when we are reconstructing the sequences, we rely on the model which we train separately. And that model, in my case, I was pre-training on the historical data which I was getting from Iceberg, which was coming from a Kafka topic. And then the result I was sending to the anomalies, and then back to Kafka topic, and that's it. So as with ARIMA, I must admit I relied heavily on the libraries for LSTM as well. There are different libraries. I had to play quite a lot with different parameters to make it make sense. And in the end, I was looking so that was stuff which actually fit the prediction, and then I had a lot of other values which were outside of that particular state. And then if you look at both ARIMA and LSTM, ARIMA is amazing for actually majority of the use cases. LSTM is more complex, might be better for some when you have a lot of different features, but ARIMA is really good because you can also track how it predicted. There is no black box magic like you have with the ML model. So yes, this is the experimentation which I have done with anomaly detection, Kafka, Flink, and Iceberg. I hope it was useful. I also have one link to share, because I saw that you have the free tickets for current, for some lucky people out of here. If you don't get those, there is also this ticket with 40% discount. And if you have any issues, also you can ping me if you have troubles using it. So that's it from me. Thank you so much for listening.